Hello everyone, this is Vijay from simulationHub team. In this video, we are going to look at how to set up a simulation problem on simulationHub. So every simulation on simulationHub is divided into 5 stages. The first stage is to upload the geometry. Once the geometry is uploaded, we need to extract the fluid domain. Once the fluid domain is extracted, we need to apply set of boundary conditions. Once the setup is done, we need to submit the simulation for solution of the equations. And once the solution is converged, we will see the results. So these are the 5 stages involved in any simulation on simulationHub. Now before looking at how to set up the simulation problem, let's look at few of the important concepts which will help you while doing a setup. The first concept is a CFD domain. So what is CFD domain? It is a region or a domain in which CFD equations are to be solved. Now this domain typically depends on what is the physics you want to capture or what is the objective of the simulation. For example, let's say we want to do a flow analysis, maybe to estimate the pressure drop or to calculate the flow distribution. Only fluid region is necessary. But if you want to do a thermal analysis, maybe to estimate temperature distribution, the fluid as well as solid domain is necessary. See, although the CAD model is same, the region or CFD domain depends on the objective or the physics that we want to solve for. The main challenge for defining a CFD domain is the complexity of the CAD model or the way the CAD model is created. Most of the CAD models available contains only the solid part. It does not have something called as a fluid region. Now extracting a fluid region or a fluid domain is complicated for complex geometries and it is a very time consuming task. So let me elaborate more on what is CFD domain. For example, I have a 90-degree elbow. The flow is coming in from the top and then it is divided into 2 branches, outlet 1 and outlet 2. Now what I want to do is, I want to find out the pressure drop from inlet to outlet 1 and inlet to outlet 2, or I would like to know how much is the flow going to outlet 1 and outlet 2. So in this case, the objective is to solve only flow equations inside the 90-degree elbow, and this becomes the CFD domain, only the inside part of 90-degree elbow. Now let's take another example. I have a same 90-degree elbow, flow is coming from the top and divided into 2 branches at the bottom. Now I would like to know the delta P as well as delta T. For example, let's say some hot water is coming in and there is a heat dissipation in the atmosphere. I would like to know the distribution to each outlet as well as what is the temperature drop when it moves from inlet to outlet. Now in this particular case, my domain is both the fluid domain inside the 90-degree elbow as well as the solid region. So flow and energy equations will be solved inside the fluid domain and the conduction equations will be solved for a solid region. So if you see, the elbow is same when we create or construct a CAD model, but the CFD domain is different and it depends on the objective of the analysis. Now let's look at what is fluid volume or what is a fluid domain. Fluid domain is typically necessary for doing a flow analysis and it is a region bounded by the wet surfaces. Let's see few examples of it. For example, let's say the objective of this analysis is to find out the coefficient of a control valve. So what I have created is an actual CAD model. The region shown in a black color is actually a CAD model and the region shown by a green color is a fluid volume inside the control valve. Now as I am interested to do only flow analysis, the CFD domain is only the fluid volume inside a control valve. Let's take another example. Let's say I want to do analysis to find out the ventilation inside a house. This is the actual CAD model of the house. It has a solid pass defining the walls. It has all other components which are inside the house. Now, as I am interested to do only flow analysis, so the region or a CFD domain is only the fluid volume inside the house marked in a green color. Let's see some details about what is the challenge of extracting a fluid volume. In typical case, there are different steps involved to extract a fluid volume. The first step is to identify all the wet surfaces in the CAD model. Then delete all unwanted parts and surfaces which are not necessary, which are not wet surfaces. In most of the cases, the wet surfaces would not be connected to each other, so we have to patch the gaps to form a closed or something called as a watertight volume, and then create a watertight volume using all the wet surfaces. So these are the typical steps involved to extract a fluid volume out of any of the CAD model, and this is really a time consuming process for complicated CAD models. In simulationHub, we need not to carry out all these steps. What we need to give is just a point which is inside a fluid volume. For example, let's say I have a house model and I would like to do a flow analysis inside the house. I just need to select 2 points so that the center point of these 2 points is inside the fluid domain. And that's it. This is the information that you need to pass to simulationHub. simulationHub takes this information and its intelligent algorithm finds the fluid volume automatically for you. If there are certain gaps or openings, this algorithm automatically identifies those gaps and openings and close those gaps to create a watertight volume. So this is one important concept about extracting a fluid volume or a CFD domain. Let's see one more important concept called as boundary conditions. So on simulationHub, you need to define at least one inlet and one outlet boundary condition. There are 3 types of boundary conditions available on inlet. One is the velocity inlet, which specifies the fixed value of flow velocity at the inlet. The another boundary condition is a mass flow inlet, by which you can define a specified value of a mass going through the inlet. And the third type is a pressure inlet, which defines the total pressure, which is summation of all form of energies, static, dynamic as well as hydrostatic energy available with the fluid. At the outlet, you need to define the static gauge pressure. So these are the 2 important concepts that you need to understand before you start setting up your first simulation. So let me give you some brief about what is the simulation setup that we are going to do now. So this is a sample model of a house. The orientation of the house is such that the wind is flowing from front to back with 2 meter per second velocity. This is the typical wind condition based on the geographical location. Let's say that this door is open, which is facing the wind. This window is closed and the 2 backside windows are open. The kitchen window and room window is open. Now what I am interested in is to find out how exactly air moves through the house if only the front door is open and the backside 2 windows are open. Now as we have defined this problem, let's set up this problem and see exactly how air moves inside the house. Now I have logged into my account on simulationHub. Let me create a new simulation. Once you create a simulation, you will directly go to 3D viewer. So the first step is to upload the model. Let me select a model which is available on my computer. Simulation Hub supports different types of file formats, but the recommended one is the step file. So let me select a step file. The time required to upload the model depends on the file size, the complexity of the CAD model, as well as the network bandwidth available with you. So now the model is uploaded. Let me do some settings to display it nicely. Now let's look at some details about this model just to understand the complexity. So the first thing is, if you see, I have intentionally closed this door as well as these windows. It's not necessary on a simulation hub that your model is closed model. If you see, this particular window is open, there is no cap on this particular window. Simulation Hub fluid volume extraction algorithm automatically identifies the openings and closes the opening. Let us see some details about this model. So this model is pretty complex. It has many parts, it has many components. Most of the components are modeled in detail. So if I want to extract the fluid volume manually, this is really a complex process for such complicated models. So the model is uploaded. So the fluid volume extraction button is active. Once I click on that button, it will ask me to select 2 points. Let me select the first point here by left mouse click. I can rotate the model by shift and middle click. Let me select another point somewhere here. And now you will see that there is a center point created. Let's rotate the model and see whether this point is inside the fluid volume. So once the fluid point is correctly created, let me click on accept, and this sends this information to Simulation Hub fluid volume extraction algorithm. Once the job is submitted, you will see a pop-up. You can continue this fluid volume extraction process, or you can also terminate it if something is wrong with your input. Once the fluid volume extraction job is submitted, you will also get an email notification about it, about when the job is submitted, and few more details about your job. The time required to extract the fluid volume depends on the complexity of the model. You need not to wait till the fluid volume is extracted. You can always switch back to your dashboard. And on the dashboard, it will show you that the fluid volume extraction stage is running. Once the stage is completed, it will highlight this button with a green color, and then you can again open the model in a 3D viewer and then carry out the further process. So now the fluid volume extraction process is completed. You can see that the fluid volume extraction button is green. Once the process is completed, you also get a notification from Simulation Hub that the fluid volume extraction process is completed. So the next step is to set up the boundary condition. So let me open this model in a 3D viewer again. So this model is open now. So let me see how exactly the fluid volume is extracted. I will hide the solid part. So you can see that the complicated fluid volume is extracted. The interesting part is it has automatically closed the window which was open. Now the next stage is to provide the inlet and outlet boundary conditions. So if you see, the boundary condition button is active. Let me define the inlet condition first. As discussed in the problem, the door is open and exposed to a wind with 2 meter per second velocity. So I'll select that face and provide 2 meter per second velocity. Similarly, let me define the outlet condition. So this window is open and exposed to a zero static pressure. Similarly, this window is also open and exposed to a static pressure. If I want to cross check the conditions, I can click on view definition and just mouse over to the faces. So this shows that it is a zero static pressure. This face also shows that it's a zero static pressure. And this is the inlet face with 2 meter per second velocity. If you mouse over to all other faces, these are walls. So as the setup is verified, let me submit this setup for simulation. Once you click on run button, it will ask you for a fluid. So in this case, air is a fluid. And it will ask you for a resolution of a mesh. Let me submit this for a coarse mesh setup. I'll click on run. So it takes all this information and submits the job for simulation. Once the job is submitted, you can terminate the job at any point you want. You can wait for the simulation to be completed on a 3D viewer, or you can go back to your dashboard. So on the dashboard, the status of this model is simulation running. Once the job is submitted for simulation, we also send an email notification about it. The amount of time required to complete the simulation depends on the complexity and the cell count of this job. So the simulation is completed now. You can see that the run simulation button and view result button is green. Once the simulation is completed, you will also get an email notification about it. So let me open this simulation to view the results. So you will notice that the view result button is active. There are three types of results that you can view. One is the flow tubes, another is the directional flow tubes, and third is the surface pressure plots. So to view the results effectively, let me hide a few parts. So this is the flow tube. So you will notice that the flow is going to both the rooms, although kitchen is getting more air compared to the room, and that is mainly because of the straight path from the open door to the kitchen window, as well as the size of the window. The size of the kitchen window is a bit bigger compared to the size of a room window. You can also view the animation or directional flow tube. Now let me take few snaps of this result by using a snapshot button. Once you click on the snapshot button, it will take the snap and download it. Let me take another snap of only flow tube. in maybe different orientation. So this is all about setting up the simulation on simulationHub. Thanks for watching this video. If you have any further question, feel free to contact us.